Hi, everyone, and welcome to my next installment in my Algebra and Precalculus video series. In this video, I'm going to be talking about the graphs of the tangent, the cotangent, the secant, and the cosecant functions. In the previous video, we talked about the sine and the cosine, and now we're going to deal with the other four. I'm actually going to split this video up into two parts. All right, so the first part, I'm going to deal with the tangent and the cotangent function. And then I'm just going to pick up where this one leaves off and deal with the secant and the cosecant in part 2 of this video. Okay, so let's start with the tangent function, and then we'll move on to the cotangent function. But to do so, we're going to have to talk about a couple of things that we have already talked about previously. One of them is graphing more complicated versions of these functions based on transformations of the simplest representation of that class of functions. So for example, to graph the first two, 3 times the tangent of 1/2 x and the tangent of x plus pi over 4, we're going to start with the graph of y equals the tangent of x, and we'll transform that graph, shift it, stretch it, compress it, reflect, things like that, things that we've spoken about previously. Same thing for the cotangent, and then the cosecant, and then the secant function. All right, so to graph the cotangent function, we're going to start with y equals cotangent of x. So that'll be the focus of this first part of the video, and then we'll deal with the cosecant and the secant later. All right, so let's start with the tangent of x. To talk about the tangent of x, we have to review a little bit of what we know about vertical asymptotes. All right, so a vertical asymptote is a vertical line, and in this case, the line x is equal to a is a vertical asymptote of the graph of f if f of x either increases or decreases without bound as the x values approach this number a. So what that means is decreases or increases without bound is the graph either goes to infinity or goes to negative infinity. And the way we find these asymptotes, and this is again something we've done previously, if you go back to the video where we discussed rational functions, for example. Right, so a vertical asymptote is when the denominator of a reduced fraction, right? So this fraction, f of x over g of x, where they have no common factors, so nothing to cancel, no common factors to cancel. If a is a 0 of the bottom, right? If a is a 0 of g of x, then the line x equals a will be a vertical asymptote of the graph. Now, why are we talking about vertical asymptotes? Well, the tangent function is a fraction. The tangent function is a fraction. We defined the tangent function as sine over cosine. Sine over cosine. And so we have a variable in the denominator of a fraction, which means the denominator may be 0, and in this case it is 0. Whenever the cosine function is equal to 0, the tangent function is going to have a vertical asymptote. And from what we know already about the cosine function, we've talked about the unit circle, we've talked about the graph of the cosine function, the x-intercepts of the cosine function. Now the cosine of x is equal to 0 at infinitely many different values. Infinitely many different values of x. And every time the cosine function is 0, the tangent has another asymptote. And since that happens every time the cosine is 0, we actually get these infinitely many asymptotes, right? The cosine of pi over 2 is equal to 0. The cosine of 3 pi over 2 also equal to 0. The cosine of 5 pi over 2, the cosine of negative pi over 2, 0. Cosine of negative 3 pi over 2, negative 5 pi over 2 is 0. So we get these zeros on the cosine function every interval of pi. So when we graphed the sine of x and the cosine of x, we saw that those graphs repeated every interval of 2 pi. Well, it turns out the tangent function repeats twice as often every interval of pi. Of course, this goes on to infinity and to negative infinity. So for the tangent function, we're going to do a couple of things. We're going to evaluate or discuss what happens at the asymptote. And then we're going to plot a couple of points. Maybe we'll plot 3 points. Okay, so what we have here is just the right half or the right hemisphere of the unit circle. Now, as the angle approaches pi over 2, remember this is an angle of pi over 2. Right? As the angle approaches pi over 2 from the left. So think about this red point as getting closer and closer and closer to the y-axis. Right? Well, the y values are getting closer. Well, I don't want to say equal to, they're getting closer to +1. And the x values, if we slide that red point to the left towards the y-axis, those x values are getting closer and closer to 0, but they stay positive. All right, so what do we get when we take the number 1 divided by an infinitely small number? Well, we get an infinitely large number. So as the angle gets closer to pi over 2 from the left, the values of the tangent function go to infinity. And then, let's erase this. As the angle gets closer to negative pi over 2, so negative pi over 2 is down here. This would be an angle of negative pi over 2, put you at the point 0, -1. So as this red point gets closer and closer and closer and closer to the y-axis, the negative rotation, well, those y values are getting closer and closer to -1. While the x values, again, get closer and closer to 0. Ooh, I should say the x values, not 0. The x values get closer and closer to 0, but also they stay positive. So really, really small positive numbers. So when you take -1 divided by, or a number close to -1 divided by an infinitely small positive number, you got a negative sign, and that number gets really big, but it gets really big in the negative direction. So the tangent goes to negative infinity. So we've talked about this before when we discuss rational functions, the behavior at the asymptotes. At a vertical asymptote, as the graph gets closer to it, the y values are either going to go up to infinity or down to negative infinity. All right, so we've got behavior at the asymptotes, and then let's talk about plotting at least 3 points. So we've got the behavior on the left. That's a vertical asymptote. The graph is going to go down to negative infinity. We've got the behavior on the right. That's that vertical asymptote on the right. The graph is going to go to positive infinity. And then we've talked about evaluating trig functions. So what is the tangent of negative pi over 4? Whoop, that doesn't look like a 4. Negative pi over 4. Well, that's the sine of negative pi over 4 divided by the cosine of negative pi over 4, and that gives us -1. Okay, so that's this point right here. When x is negative pi over 4, the tangent of x, or when theta is negative pi over 4, the tangent of theta, whether we use x or theta doesn't matter. The y value, or the function value, is equal to -1. If we evaluate the tangent of 0, that's the sine of 0 divided by the cosine of 0, we get 0. That's this point. And finally, if we evaluate the tangent of positive pi over 4, that's going to give us +1. The sine of pi over 4 divided by the cosine of pi over 4, we get 1. And so we could have plotted more points. We could have also let theta equal pi over 6 and negative pi over 6 and pi over 3 and negative pi over 3. We would have gotten more points on the graph. But this is enough between the end behavior and a few points. And so it turns out that the tangent function will have a graph that approaches -infinity on the left, crosses through these points, and then approaches +infinity on the right. And so that blue graph, and it's a little wiggly on the right. Let me redraw this. I'm going to go up, cross, 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 and then up. All right, so that blue graph, that is the graph of the tangent of x. Or if you're using theta as your variable, the tangent of theta. So we could graph more complicated tangent functions by starting with this guy, starting with the simplest version of the tangent function, just tangent of x. And so what we did, let me go to the next slide. What we did with the sine function, we graphed one period and we saw that the graph repeated to infinity to the right, -infinity to the left. The tangent function does the same thing. And on the previous slide, we just graphed that first, I don't want to say first, but that portion of the graph between -pi over 2 and pi over 2. Then we got another copy over here to the right, another copy to the right, another one to the left, another one to the left, and it keeps going infinitely in both directions. Now, the way we graph the sine function, let's say, for example, we had y is equal to a times the sine of bx plus c. This was the subject of the previous video right before this one. We graphed the sine and cosine functions. So we graphed y equals a times the cosine of bx plus c. We talked about change in amplitude, change in period, change in phase shift. All right, so that was the a, the b, and the c. All right, so we got the same thing here. We're just talking about the tangent function this time. Okay, so here's a good two-step process. It's got maybe more than two individual steps in here, but I'm going to generalize it as a two-step process to graph the tangent function. So step one is find a period. Find a period that contains two asymptotes. So we want an asymptote on the left, asymptote on the right, and then the graph that goes between them. All right, so find a period. And the way we find the period, well, that's going to be just like with the sine and cosine functions, coming from the values of b and c, whatever they may be. And so the way we're going to do that is solve for x. Solve this inequality. We say, well, the angle or the argument of this tangent function, bx plus c, well, the basic tangent function, the simplest version, we graph that one period from -pi over 2 to pi over 2. So there's going to be a possible, potential change in the period. Now, once we have that, we're going to split the period up into 4 equal parts. And I'm going to call those numbers, let me use a pen here, those numbers that separate those 4 equal parts. I'll just call them, because they're going to be x values. So I'll call them x1, x2, x3, x4, and x5. So the first and last, the x1 and the x5, those are going to be asymptotes, the vertical asymptotes, right? X1 is the vertical asymptote on the left, x5 is the vertical asymptote on the right. And then we've got 3 points. 3 points on the graph. And that's going to correspond to the change in amplitude. So instead of that, those points we graphed in the previous couple of slides, negative pi over 4 comma negative 1 and positive pi over 4 comma positive 1, well, there might be a vertical stretch. And that comes from a change in, we call that a change in amplitude, so that value of A. So at x2, there's going to be a point, and that's going to be the point x2 comma negative A. And negative A, it's the A that's coming from the function. X3 is going to be the x-intercept, x3 comma 0, and then x4. If A is some number other than 1, then that's going to be stretched as well. That y value is going to be stretched, and that's going to be the point A4 comma positive A. Okay, I think it might be easier to see what's going on here if we do an actual problem. Right? And then if we need to, we could graph additional periods by first graphing one period and then just making copies of that period, as many as we need, either to the left or to the right. Okay, so let's look at this function. Y is equal to negative 3 times the tangent of 1/2 x. Now, if we look at this and compare it to that model, y is equal to a times the tangent of b times x plus c. Well, what are the values of a, b, and c in this problem? Well, a is negative 3. Right? B is 1/2 because we've got 1/2 x. And c, well, there is no plus or minus term in the tangent function. So in this case, c is going to be 0. So let's start with bx plus c is between negative pi over 2 and pi over 2. We're always going to start with negative pi over 2 and pi over 2. And now solve for x. Well, what is the b and the c in this problem? We've got negative pi over 2 is less than or equal to. The b is a half, so that's 1/2 x. There is no c, or c is 0. So you could put a plus 0 if you want. Don't need to, but there's nothing wrong with putting a plus 0 there. And now solve for x. Got to get x by itself. Well, there's a 1/2 in front of the x, so we could get rid of that 1/2 by multiplying everything by 2. Multiply the left, multiply the right, multiply the middle, all by 2. And so negative pi over 2 times pi will give us negative pi is less than or equal to x is less than or equal to positive pi. Right, so that is our new period. From negative pi over 2, or sorry, negative pi to positive pi. So now we got to split that up into 4 quarter periods, or 4 equal pieces. So the easiest way I think to go about this is to cut it in half. So it's halfway between negative pi and positive pi. Well, it's going to be 0. And then, cut this one in half. What's halfway between 0 and pi? Well, that's going to be pi over 2. And what's halfway between negative pi and 0? That's going to be negative pi over 2. Right, so those are those 5 values, x1, x2, x3, x4, and x5. So if x1 is negative pi, that is a vertical asymptote. If x5 is positive pi, that is a vertical asymptote. And then we've got these 3 points. It's x2 comma negative a, x3 comma 0, and x4 comma a. And so we've got the point negative pi over 2 comma negative a. Well, go back to the original problem. A is a negative 3. So negative a would be a negative of a negative 3, which would be positive 3. So there's 1 point. X3 comma 0, so that would be 0 comma 0. That's a point. And then x4 comma a would be pi over 2 comma negative 3. All right, so we got 3 points and 2 asymptotes. 3 points and 2 asymptotes. And that's enough. That's enough information to give a graph of the tangent function because we know what the shape of the graph is. The tangent function always looks. What happened to my pen? There we go. The tangent function always looks like this. Unless there's a reflection over the x-axis, in which case it would look like this. It's going to have one of those 2 shapes. Right? So there's point, 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 3 points, 2 asymptotes, and that is enough to draw the graph of the tangent function. So that red graph, I think on my next slide it's blue, but that red graph is going to be the graph of negative 3 times the tangent of 1/2 x. The tangent of x starts down on the left and then goes up. But because of that negative out front, we get a reflection over the x-axis. That's why in this example, problem number 1, it starts up on the left and down on the right. All right, so there's going to be our graph. Okay, problem number 2. This one's going to incorporate a phase shift. We got a plus pi over 4. All right, so I'm going to start the same way. Use that model, y equals a times the tangent of bx plus c. Well, what is a, b, and c in this problem? Well, a is 1 because there's no coefficient in front of the tangent, so it's just 1 tangent of x plus 4, x plus pi over 4. Right? The b is also 1, and the c is pi over 4. So when we set up bx plus c, remember this is always step 1. Bx plus c is between negative pi over 2 and positive pi over 2. The bx plus c is whatever's in the parentheses. Right? So that's going to be x plus pi over 4. Now solve for x. Well, get x by itself. We got to get rid of that plus pi over 4. So let's subtract pi over 4 from the left, from the right, and from the middle of this compound inequality. And so that pi over 4 and negative pi over 4 in the middle will cancel. So we'll get x. On the left, we got negative pi over 2 minus pi over 4. So that's like negative 1/2 minus 1/4. That'll give us negative 3/4, or negative 3 pi over 4. And then on the right, 1/2 minus 1/4, pi over 2 minus pi over 4, will give us positive pi over 4. Right, so x1, the beginning of the period, is negative 3 pi over 4, and then x5, the end of the period, is going to be positive pi over 4. And what's halfway between them? Well, that's the average. You add them up and divide by 2, or by whatever method you like to find the halfway point. That will be negative 1 pi over 4. So I like to do it this way. Take the whole period, cut it in half, and then take each half and cut it in half. So halfway between negative pi over 4 and positive pi over 4 is going to be 0. And halfway between negative pi over 4 and negative 3 pi over 4, well, that's halfway between negative 1 and negative 3 is negative 2. So that's negative 2 pi over 4, which becomes negative pi over 2. All right, this part right here, a lot of times, like, this is the most difficult, not difficult, maybe difficult, but also the most time-consuming part of the problem, getting these 5 numbers. So now we got x1, x2, x3, x4, and x5. And what we do with these numbers, now let me go back a few slides just to remind everyone. X1 is an asymptote, x5 is an asymptote, and x2, x3, x4, those 3 numbers in the middle give you 3 points. x2 comma negative a, x3 comma 0, x4 comma positive a. All right, 2 asymptotes and 3 points. All right, let me go back. We'll finish up this problem. Oh, there we go. All right, so we got vertical asymptote, vertical asymptote. And then we've got the point x2 comma negative a, x3 comma 0. We're not calculating these y values. We're just using what's these values of a, b, and c. And then x4 comma positive a, so 0 comma positive 1. So we got 2 vertical asymptotes, 3 points, and we know the shape of the graph between those 2 vertical asymptotes. So now I think we're ready to put this together. On the graph, we've got asymptote, asymptote, 3 points. And this is, again, negative pi over 2 comma -1, pi over 4 comma 0, and 0 comma +1. And once we have those 3 points, we know the shape of the tangent graph always looks like this. All right, so there's our final graph. And this is not the only method, this 5-number summary where I use 2 asymptotes and 3 points by breaking the full period up into 4 equal quarter periods. But I like this method. I think this is like once you get this down, it works for every tangent graph and every cotangent graph. We're going to use the same exact approach for the cotangent function. And actually, in the next few slides, you're going to see some repetition, right? This is the same slide from earlier on, except instead of graphing the tangent function, we're graphing the cotangent function. But the cotangent function has asymptotes as well because it's a fraction. The only difference is the tangent is sine over cosine, and the cotangent is the reciprocal. Cosine over sine. So whenever the sine function is 0, the cotangent function gets a vertical asymptote. Whenever the sine is 0, 0 on the bottom of a fraction, you get a vertical asymptote. So the sine of 0 is 0. Sine of pi is 0. Sine of 2 pi is 0. Sine of 3 pi is 0, and so on. Sine of negative pi, negative 2 pi, negative 3 pi, all 0. So this is something I'm not going to spend too much time talking about, like how to evaluate the sine of pi and the sine of 2 pi and the sine of 0. That happened a couple of videos back. But we're building on that. We're building on all of this stuff. Okay, so now for the cotangent function, I'm going to look at the top half of the unit circle. And the reason I'm looking at the top half is because at this point right here, which is 1 comma 0, we get a vertical asymptote. And at the point -1 comma 0, we also get a vertical asymptote. So I'm looking at a portion of the graph that's stuck between 2 vertical asymptotes. I don't want to look at half of the graph to the right, half to the left of an asymptote. I want to just look at one continuous piece of the graph. So as the angle approaches 0 from the right, let me erase some of this. I don't want it to be too cluttered here. So as this point gets closer and closer and closer to the x-axis, meaning the angle is getting closer and closer to 0, the x values are getting closer to 1. And the y values, remember, cotangent is x over y. So the x values are getting closer to 1. The y values are getting closer to 0. But those y values are positive. So we're getting a number close to 1 divided by an infinitely small positive number. So at that asymptote, the graph, the y values are going to go to positive infinity. By that same reasoning, as the angle goes to pi, remember pi is 180. That's an angle of pi. An angle of pi puts you at this point right here, -1 comma 0. So as this red dot, this red point gets closer and closer, traveling along the circle, as it's getting closer to the point, negative 1, 0, those x values are getting closer to negative 1. And those y values are getting smaller and smaller. They're getting closer to 0. But again, they are all positive, really, really small positive numbers. So when you take a negative 1 divided by a really small positive number, you get a really big negative number. So the graph goes to negative infinity. So it's just the reverse of what happened with the tangent function. And we're going to take the same approach. So we've got a vertical asymptote. As we get closer to 0, the graph is going to positive infinity. We've got another vertical asymptote. Right? Okay, this is the same x1, x2, x3, x4, and x5, right? That's 0, pi over 4, pi over 2, 3 pi over 4, and pi, right? Those 5 numbers, right? As the angle is getting closer to pi, or the x value is getting closer to pi from the left, the graph is going down to negative infinity. And so the cotangent graph is going to do the same thing as the tangent graph. It's going to hit these 3 points. Same shape as the tangent graph, just a reflection. And we're going to graph more complicated versions of the cotangent graph in exactly the same way. Exactly the same way as we graph the tangent function. Right, we're going to look at one period. And if we need more periods, and we just graph one, and then we copy it either to the left or to the right, depending on the problem. In this video, I'm just graphing one period. So again, this is the exact same slide. Just almost the exact same slide. Just very, very slight difference. Instead of at the very top in this blue bar, instead of saying to graph one period of the function y equals a tangent of bx plus c, now we're looking at the cotangent of bx plus c. And the only difference is right here. For the tangent function, that first point is x2 comma negative a. And the fourth x4 would become a positive a. For the cotangent function, those two are switched. Okay, that's the only difference. So we find the period. We split the period up into 4 equal parts. And those numbers that separate those 4 equal parts, those 5x values, the first and last are the asymptotes. And the 3 in the middle are 3 points on the graph. 3 points on the graph. All right, so let's look at this guy. Let's look at this guy. We graph the function y equals 1/2 cotangent of 2x. Oh, let me go back one slide. I need to highlight one more thing here. Because we looked at the top semicircle from 0 to pi for the cotangent function. And so let me write in red what the tangent function was. Nope, that's highlighter. In red pen. Okay. When we were graphing the tangent, so a times the tangent of bx plus c, this was a negative pi over 2. This was a positive pi over 2. This was a negative a. And this was a positive a. Right? So we're taking the same approach. We're doing things the same way. We're just some slight differences with the numbers when we're dealing with the cotangent versus the tangent. Everything in the green is the cotangent function. In red is the tangent function. Easy to make a mistake here if you don't have this sort of written out in front of you or memorized, one or the other. No need to memorize it. You could just write it down or just refer to these slides. All right, so 1/2 times the cotangent of 2x. Step 1 is always step 1. Figure out the period. So we're looking at this model, y equals a cotangent of bx plus c. Say the same thing as I did for the first problem and the second problem. What is a? What is b? And what is c? Oh, we just match up the numbers. In this case, the a is the 1/2, the number in front of the cotangent function. The b is a 2, so we have 2 times x. And the c, just like in the first problem, c is 0 because there is no plus or minus term in the cotangent function here. So we'll start with bx plus c is between 0 and pi. Between 0 and pi. Now, what is the bx plus c? Again, bx plus c is whatever's in the parentheses in the problem. In this case, it's 1/2 times the cotangent of 2x. So 2x is the bx plus c. 2x is the bx plus c. Got to solve for x, get x by itself, so we could divide everything. Oop, I said pi, but I wrote 0. Hang on, let me fix that. That should be a pi. Divide everything by 2. 0 divided by 2, well, that's still 0. 2x divided by 2, that's going to give us the x, which is what we want. And pi divided by 2 is pi over 2. And so this is the period. We are going to graph one period of the cotangent function. And that's going to be stuck between x equals 0 and x equals 2 pi. Those are our two asymptotes. Okay. So again, take the period, which is 0 to pi over 2, and split it up into 4 equal pieces. So just like in the last two problems, I like to cut it in half. So halfway between 0 and pi over 2 would be pi over 4. Halfway between 0 and pi over 4 is pi over 8. So this is 1 over 8, 2 over 8. This would be 3 over 8 and 4 over 8. So that last value is going to be 3 pi over 8. Vertical asymptote, and then 3 points. x2, comma, a. So that's pi over 8, comma, a, which is 1/2. That is 1 point on the graph. x3, comma, 0. So that's pi over 4, comma, 0. That is another point on the graph. And then x4 comma negative a. So that's going to be 3 pi over 8 comma negative a. So negative 1/2. And that a is the vertical stretch or the vertical compression. So instead of ones, we're going to get 1/2. All right, and that's enough. We've got 6 things right now. We've got 2 vertical asymptotes. We've got 3 points, and we know the shape of the cotangent graph. It's going to look like this. So let's put all of that on the coordinate plane. X1, X2, X3, X4, and X5, taking that period, splitting it up into 4 pieces. We plot the 2 asymptotes. Then we plot the 3 points. And then we draw the graph. And that should do it for the graph of the 1/2 times the cotangent of 2x. So we start with the period. We find the period by solving that inequality. Then we cut the period up into 4 pieces, 4 quarter periods. Then once we have that, we've got 2 vertical asymptotes. We've got 3 points. And once we have that, we are able to draw the graph. Okay, that's 3 examples. It's going to take a couple more, few more, half dozen more, baker's dozen more, however many it takes. At some point, you do enough of these and it starts to click. That, these aren't easy problems, but I will say it is, one of those situations where every problem is done the same way. Every problem is done the same way. So in cases like this, a little bit of repetition, it really helps add to the overall understanding and level of comfort with this material. Okay, I'm going to stop here in terms of problems. If we keep going on the slides, now we're going to get into the cosecant function and then the secant function. All right, but I'm going to stop here. We'll call this part 1 of the video. Feel free to just close this and open the next one up right away. This is going to be a continuation. So at this point of those 6 trig functions, in the last video, we talked about the sine of x. Then we talked about the cosine of x. In this video, we talked about the tangent of x. And then the cotangent of x. So check, 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 and check. And the last 2 are the secant of x and the cosecant of x. So we've got 4 down, 2 to go, and then we'll be done with graphing the 6 trigonometric curves. All right, that's it for now. I hope this was helpful.